Right, so today we're going to look at some sort of other applications of physical systems where we can solve a problem or understand what's going on by using an application of moments. And so the first thing we'll do is let's deal with our first one, which is a very simple bridge. So a very simple bridge. And the way I'm going to design this bridge is I'm going to have a support beam here, and I'm going to have my bridge like this. So I've got pillar A, and I've got pillar B, and I've got a plank going across the two. Now, in order to keep this sort of simple, what we're going to have is we're going to have an object. And let's say this object has a weight of 2,000 newtons. And this object is going to cross the bridge. And let's say this bridge is 5 meters long. So my object is just going to move across. I mean, at this point we can all think, wouldn't it be exciting if I was able to draw more exciting things than boxes? And this bridge does not collapse. It doesn't break. So the question we've got is, okay, if it doesn't break, well, if I've got my object sitting there, it doesn't break. Well, and it's, that means that this force of 2,000 newtons, well, that's going to have to be supported. Let me move this to the side for a moment. It's going to be supported. No, I've made it red. Oh, that's exciting. That wasn't what I expected to do, but let's go. It's going to be supported by a force upwards from support A and a force upwards from support B. And in order for this thing not to, this thing to be stable, what we should be able to work out, or hopefully it should be fairly clear, that these two forces, force A and force B, should equal 2,000 newtons, okay? Or whatever the weight of this object is, okay? They react. They are a reaction force to the weight of the object. If the object is 10,000 newtons, then they would add up to 10,000 newtons. And essentially, up until a point where my object gets too big, if my object is too big, and my pillars can't support that, at that point my bridge is going to break. So if the maximum, if I get 1,000,000 newtons and my support simply can't provide that reaction, that's when my bridge is going to break and it's all going to be destroyed. But the question that we want to ask ourselves is a little bit more subtle than that. It's this idea of, as we travel across the bridge, how do these two forces change? If we start with a very simple scenario, there should be 3 scenarios that should sort of be a bit intuitive. The first is, what happens if my object is here, sitting on top of sort of like pillar A? Well, in that case, pillar A should be providing all of the support, okay? Pillar B will have no idea. So here, my reaction force would entirely be on pillar A. Over here, that reaction force would entirely be on pillar B. In the middle, we would hope that my forces should be equal. So the force of A and the force of B, they would each be 1,000 newtons. So we should have this scenario that as we move across, the load is more borne by the pillar that you're closest to. Then you get to the middle, where it'll be half and half, and then you get more support on that one here. But let's put it here. Let's put this object, let's say we are, let's deal with a distance. Let's say we are 1.5 meters along. Okay, so our object is 1.5 meters along the distance. question is how are these two forces distributed? What is the size of the forces in both? And we can solve that problem using the principle of moments. Okay, so remember, the principle of moments is that clockwise moments equals anti-clockwise. And this looks a bit like a seesaw, but the problem with it, the difference with being a seesaw is that, hang on a minute, I've got more than one pivot point. I've got more than one. How do I know what I pick? And what's wonderful is I can pick anywhere. I can actually pick anywhere, but I'm going to pick something very simple. I'm going to show that it gets the same answer, but I'm going to say, right, let's say that this is where the pivot is. The pivot is at pillar A. Okay, and I'm going to use the principle of moments, and I'm going to say, right, so I should have clockwise and anti-clockwise. Now, what do I need to worry about? Well, remembering that a moment is equal to force times the perpendicular distance from the pivot, I'm going to make this problem a bit simpler. It turns out I do not need to worry about this force. I don't need to worry about force A because the distance of that force from pillar A is 0, so it's going to generate 0 moment around that point. If I pick that point, it generates 0 moment. I don't need to worry about it, which is wonderful. So what I now have is I can worry about the weight of the object and force B. So let's look at what we have. We have, from this, we've got a moment pulling in this direction, which is 2,000 newtons times 1.5. And so 2,000 newtons times 1.5 is equal to 3,000 Newton meters. And that's that one. And we know that it has to be balanced by an anti-clockwise moment going in the other way, remembering that this is our pivot. And this one is force B times 5 meters, and that has to equal 3,000 Newton meters. So I can now basically start equating these things. So I know that the clockwise moment, which is coming from my weight, so that's 2,000 times 1.5, which equals 3,000 Newton meters. Going into green for that, so anti-clockwise is equal to the force from pillar B times 5 meters, and I know that this has to be the same. That's got to equal 3,000 Newton meters. So that leads to this idea that the force from pillar B reacting is 3,000 over 5, which is 600 newtons. Now, concept check. Does this sound about right? Well, if we think about what we talked about was going to happen, the overall weight is 2,000 newtons. We know that the pillar it's closer to should be providing more of the reaction force to it. It's closer to A, B's further away. So yeah, 600 is about right. So force B is equal to 600 newtons. And as we know that the two forces, force A plus force B equals, not 600, sorry, equals 2000, which is the weight of the box. We can now say, okay, so force A is equal to 2000 minus 600, which equals 1400 newtons. And so that is how that is derived. That's how we work these things out. Now, seems about right, but let's say, does it work? You know, what would have happened had I taken this point? Let's imagine that I'd set B as being the pivot, and you can do that yourself. Now, think about how would your equation have looked if you, instead of taking the pivot there, you took the pivot at point B. So this becomes 3.5 meters. Do you get the same values if you take the pivot at the far pillar, and do you get the same values for the different forces? So pause the video, give yourself a quick go at that, and then I'm going to work it through. Well, let's see the solution. So in this case, we're taking moments. We're going to imagine our pivot at B. So in this case, what we have, I'm just going to redraw it very quickly. There's A, there's B, there's our box. So we have a box, a distance of 3.5 meters, and we have a distance to A of 5.0 meters. And we've got a reaction force from force A, and we have a downwards force there of 2000 newtons. There's our problem. We're taking our pivot as being at that point there. So we have running in this direction, which is the anti-clockwise moment this time. So the anti-clockwise moment is 2000 times 3.5. So we get 7,000 Newton meters from that one. The clockwise moment, which is from force A acting in that direction, we would get force A times 5, and in order for this thing to balance, that's also got to equal 7,000 Newton meters. And so if we do force A is equal to 7,000 over 5, and yet again that equals 1400 newtons. So therefore force B must equal 600 newtons. And that's how we can solve the problem. It's a very, very nice thing to realize that you don't have to see immediately a pivot, but you can just take them. You can sort of pick a point and go, I'm going to work from here. By doing so, you can make the problem a bit simpler and a bit easier. Now, there is a bit of a shortcut to this. Okay. There is a shortcut method, which is that to recognize that the weights are distributed in terms of the fraction of the distance that you are along. Okay, so if we start at point A, so we start at point A, when our weight is here, it's bearing 100% of the load. And when the weight is here, at B, force A has become 0. There should be none of the load should be there. And in this case, we are 1.5 out of 5 meters along. Okay. So what we have is in this method, so we've got force A, we've got force B, got a total distance of 5, but our box has gone 1.5 meters. So the box is 1.5 over 5, so 1.5 over 5, which is 30% of the way. Okay, and that means that the load will become distributed in that ratio. So the load is distributed in a 70-30 split. And just by simply thinking about, well, which side has the bigger one, it is the one that's closer. So this will have, we're 30% of the way, so this one will get 30% of the force, and therefore we can just simply do a quick sort of calculation that 70% of 2,000 is 1,400 newtons. 30% of 2,000 is 600 newtons. And those are our load distributions. So there's different ways to think about it. You can approach it via using the moments, and you can work it out, and you can say, haha, right, okay, I've worked all this out. But you can easily also just think about it in terms of the distribution between the loads between two different pillars. And naturally, if you invent a more complex bridge with more pillars and more support infrastructures, then yeah, the loads become slightly different. You know, you've got to worry about more things, but the principle can still be the same. It just takes a bit longer to do. But at GCSE, you're only ever going to have a beam that's supported at two ends, either, you know, by having two sort of concrete pillars under the bridge, or maybe two cables, one at each end, that are holding it up. But the principle every time is the same. The closer you are to the support, the more of that weight is supported there. And there we go. That is how we solve problems involving bridges. Now let's deal with problem 2. And that is to do with stability. Okay, so stability is something that is important. And I'm going to introduce a simple reference to something that everyone, despite being told not to, will have always done. And it is that thing where you lean back on your chair. So everybody at some point has done this. The bit where you push off and you're leaning back on your chair, and you naturally try and balance yourself, and you will do that by moving your body slightly forward or slightly back, because you're looking for a moment, a thing of what we call stability, which is where your chair doesn't go one way and doesn't go another. And it turns out it's not very easy to do, and you'll find yourself doing the wrong thing, because if you go too far in one direction, you'll find your chair goes that way. If you go too far in the other direction, you'll find your chair goes back forward. Just for reference, this is a safe movement. This would be not safe. You are not being encouraged to do this as an experiment now. Please don't. Now, in order to sort of give a bit more sort of context to this in a wider world, I'm going to want you to pause the video, and there's a link to a thing called the Aldenham bus test, Aldenham tilt testing, where they do a similar thing, but with buses. So have a quick watch of that, and then we'll explain what's going. So there is a thing where any very, very large sort of object is obviously very sort of complicated. So I have a big sort of object. It's difficult to deal with this as a physical object. Okay, it becomes very, very, very hard to deal with a large number of solutions of something of a very, very definite size. In physics, what I want to know instead is how can I simplify this problem? And I can simplify a problem by finding what we call the center of gravity. And that is the point somewhere in this object, let's say it's here, where all of the weight of that object essentially acts. It's the point through which the weight of the object can be thought of to act. Is that if you kind of took an average of all of the stuff that's to this side, okay, and all of the stuff to this side of this object, and I said, right, okay, well, what's kind of the average of all this going on? It would be here. If I sort of balance it and zoom it out, that's the point at which the weight of the object appears to act. And that's kind of important, because if I take this weird object, so if I take an object and I stick it on a table edge, okay, and I'm going to try and redraw this but smaller. Okay, and I'm going to say that my center of gravity is there. I'm going to keep my yellow side and my blue side. Well, what I can think about is what's going to happen to this object based on moving it around. Yay. Oh no, I've taken the whole thing. That was annoying. No, go away. Don't want to do that. Oh, my pen's run out. Yeah. So this is why it's to do with stability. If I have an object and I've got it resting on the table, it's here, then I can imagine, oh, that was annoying. I can imagine that my pivot, I can imagine a pivot as existing here. And what I can do is I can solve a problem about whether or not this thing is going to tip off the table edge. Because as long as my center of gravity is to the left of my pivot, which is marked in yellow, then I've got a turning moment which is going to drag this object through the table. And what that means is that I'm not going to fall off. And as long as if I eke out and eke out and eke out, eke out, this becomes the critical point here. If my center of gravity is sitting down on top of the pivot, then my object is still balanced. But the instant I try and move this further, let's say I move it to here, and I'm trying to rest it here, what I now have is a turn. I've got an unbalanced turning moment. I have my pivot, which is the corner of my table, and I've got a little distance there. And so suddenly what I've got is a turning moment that is pulling that way, and my object will tumble off the edge of the table. And the reason for knowing about the center of gravity is I don't need to worry about all the different parts of this object. I don't need to worry necessarily about what it looks like. I don't need to worry about, many things. I just need to know, where is the center of gravity? How far can I push this until it falls over? Now, why is that important for the case of you tilting back on a chair? Well, you and the chair have a center of gravity. Let's assume that it's about here. Okay? And when you lean back on your chair and, take fate into your hands, what you are doing is you are looking for the point. There is your pivot. It's that back leg, the only leg that's still in contact with the floor. And what will happen to you will depend on whether your center of gravity is this side of the pivot, in which case you'll go that way, or when you bring it to this side of the pivot, in which case you'll go that way, because you will sum up all the weight, all the moments either side of the pivot, but due to bits of the chair on either side, and actually we can just solve one problem, which is where is the overall center of gravity and what does that mean? And you will know from memories of doing this is that if you feel you're going too far to this side and you're going to feel, oh no, I'm back, so you naturally lean yourself forward that way. Normally it's a quite sudden movement in order to bring your center of gravity, to move it in this direction, to move it to the left of this pivot, to mean you will lean back forward. If you fail to do that, if you fail to go backwards enough, then what will happen is you will fall. And so when you do this, this is an example we call an unstable equilibrium, because it's finely balanced and any tiny fluctuation to the left or to the right will mean that you will either go, forwards or backwards. It's quite difficult. You can't really balance in this kind of way. And so this is how that's important. Now, how do you find the center of gravity? Okay, so and this is the actual bit you need to know, really. There are two methods, really. The first method is, if the object is symmetrical. Okay, so if an object is symmetrical, you can simply use lines of symmetry. So if you've got a rectangle, you can draw a line of symmetry there and a line of symmetry there, and it's where the lines of symmetry cross. If you have a circle, well, obviously it's going to be a line of symmetry in either direction. So if you can draw lines of symmetry, and provided you've got a uniform kind of object where it's a simple shape, it's all made out of one material, you haven't created it where for some strange reason you've added a lead weight to this point here or something, then that's easy enough to do, and you can just draw a line of symmetry, and that will be where they cross, will be where your center of gravity is. The second thing is if you've got a non-symmetrical object, or you've got a slightly more complex object, let's say you've got an object like this, is what you do is you make a hole in it and you suspend it. So you make a hole and you suspend it, and what will happen is the object will rotate until this hangs below. Let's say the center of gravity is there. The object will rotate until, now I've got to try and draw this thing to the side, so it will look like, I wish I could rotate these things, so I'm going to do, that's terrible, there's my pivot, and there's the center of gravity, and what will happen is the center of gravity will run in a straight line beneath your point of suspension. And then what you can do is you suspend it, you repeat it in a different place, allow it to freely suspend, and you'll get another line, and what that will do is it will run through where those two lines intersect. That will be your center of gravity. So to find it for an oddly shaped object, what you do is you suspend the object, to freely rotate, draw a vertical line, beneath the suspension, and then you do repeat at a different point. So then finally you can say that centre of gravity is where the points, where the lines cross. And that is how you find the centre of gravity. In terms of what you guys are doing it for, you need to find the centre of gravity. You need to know how to find the centre of gravity. And ultimately, what this means is it's more a description of how you find them and what this allows us to do. And what it means is that you can have a more complex moment problem. So you can have a more complex moment where you might include the weight of the actual object itself, like the bridge. So you might have an example where you have some kind of, say, a diving board, and you've got a person who's there. You've got a force that's keeping the thing up. So you've got a force that's keeping up the diving board. You've got the force of the person. But you might know, if you've got the centre of gravity and the weight of the board itself, you might also have the force of the board. You've got this force of the person, and finally you've got a sort of reaction from this pillar, which is keeping the whole thing like stable, and then you've got your then you can take a pivot as being there. So you can have an example like that, or you might have a seesaw which is off center. So you could have a person on that side, a person on that side, and also the weight of the object, weight of the board. And that's if they ever give you an example of something which is off center. Knowing where the center of gravity is just means that you then take the weight and have to account for that moment as well. So in this case, we've got two moments acting in that direction from the person and the weight of the board, and they would have to be balanced by the moment from this person on this side as well, even if you just take it from the pivot. And there we go. That is how we can look at some slightly more